Hello, all of you wonderful people, and Dr. Hedengren, because you might be the only person who watches this. This is our process control project. It's the diver. I'm Zach Driskell,
I'm Rebecca Walker.
and let's dive in.
So our project idea is to create what we're calling a diver's jetpack. The purpose of this jetpack is to allow a diver to safely ascend from a recreational scuba dive to avoid the diver's decompression sickness, or the bends. Diver's decompression sickness occurs when a diver ascends too quickly from a dive and it causes buildup of nitrogen gas bubbles, and they can be very, very painful. They can cause itchiness, rashes, or even death in extreme cases. So our aim is to design and simulate a PI controller that allows us to set the velocity of the ascension and to be carefully controlled by this diver's jetpack. The jetpack will allow extremely small changes in velocity and acceleration to account for various disturbances that the diver can experience during a recreational scuba dive. So the math for this particular problem came from our force balance. If we have a diver underwater, he's experiencing all sorts of forces. He has the pressure of water on top of him, all the equipment he's carrying, friction or drag force, and then you have also buoyant forces and the jetpack trying to push the diver up towards the surface of the water. You can see in our equation, the first term is the buoyant force. It's pushing the diver up. We have the gravitational force pushing the diver down. That's from all the water in the atmosphere on top of him. The acceleration, which is caused by the jetpack. And then we also have the coefficient of drag right there, that C of D term. And that is our drag force that the diver is experiencing by having upward motion in water. The impact of this is that divers usually carry dive tables, and they're very familiar with this, based on how deep and how long their dive is. Depends on how quickly they can ascend and how long they can be at these pressures that the water's exerting on them. So if we can eliminate the need for these, the diver can spend more time underwater enjoying their scuba dive. These are some various assumptions that we made. We said that the mass of the diver was 70 kilograms and the equipment was 25 kilograms. Based on a theoretical model of this jetpack, we decided that it would be about 9 kilograms in weight. The water density we assumed to be a perfect 1,000 kilograms per cubic meter, and we added weights. Otherwise, the buoyant force would overcome the diver and he'd shoot straight up. Most divers do actually dive with a weight belt or weight vest so that this doesn't happen.
And that brings us to the simulation. So that equation we saw a minute ago, we made a function in Python and modeled the system. So our goal was to make him neutrally buoyant at an actuator acceleration of 0 so that there's 0 velocity. And that's what we see here in figure 1. Now you can see it's essentially 0 at 0 acceleration, which is exactly what we want with that added 0.5 kilograms for neutral buoyancy. And we ran this through step test as well just to see how the system would respond and to make sure our function behaves the way we expect it to. So from 0 to 10 seconds, 0 acceleration. 10 to 20 seconds is 0.5 meters per second squared. And then it jumps up to 1 meters per second squared from 20 to 30. And then back down to 0 for the rest of the time. And it behaves just as you'd expect it to, going faster and leveling off just due to the balance of forces. And so once we found an accurate function, we needed to get some tuning parameters so we could develop a PI controller. And we did this with an FOPDT graphical fit. So we found our gain just by taking delta y dividing by delta u. This was a step of 0.5 meters per second squared. I'm starting from 0 meters per second squared. So that gives you a gain of roughly 3. I think it's a little bit less. Tau I is roughly 2 seconds, and theta p is assumed to be 0 since the velocity responds immediately. So using these tuning parameters in our PI control, we get some pretty aggressive overshoot. It meets the set point well, but we don't like the fact that he goes too fast at the beginning. It breaches that set point. So we made our parameters a little less aggressive, and this helps the overshoot quite a bit. So we cut our gain down by 1/3, and it meets the set point much more gently, as you can see in the acceleration graph on the far right, and then levels off pretty smoothly. And it's worth mentioning, we did add some anti-reset windup to the system so that the acceleration can't exceed 2 or -2 meters per second squared. So it can't be greater or larger than either of those values. And so it's great at maintaining a set point. It can also do negative velocities in case you have a positive upward disturbance, just so we can make sure and account for any errors in the system. So the actuator can go either direction. So this is more of a start for us. If we had more time, more resources, we would make a more robust model so that we could implement a safety stop. Occasionally divers need to just take a break in their ascension so that they can do so safely. We would do an automatic shutoff at the surface, so the pressure, when it reads atmospheric, would automatically cause the system to come to a halt so that the actuator doesn't just keep running. And lastly, we would model the displacement of the diver based on pressure change. So we don't have to use a flow meter or anything like that, so you don't have so much equipment.
The big picture. We were able to develop a simulation and a PI controller, along with some tuning parameters that allow for a diver on a recreational scuba dive to safely and automatically ascend from their dive.